Unique factorization domains, Euclidean domains, and principal ideal domains, PIDs. Okay, let's start by talking about UFDs, unique factorization domains. So an integral domain is called a unique factorization domain if every non-zero, non-unit element A of the domain has an essentially unique factorization into a product of irreducibles. So A equals P1 times P2 times ... up through Pk, where P1 through Pk are irreducible elements. So by essentially unique, we mean that if A had a second such factorization, then it must just be a permutation of these primes, the same set of primes, up to unit multiples. So there's got to be a permutation sigma of 1 through k, such that if you just rearrange the subscripts and you throw in some units u sub I, pi is just unit multiples of the permuted primes. So for instance, in the integers, when I consider the factorization of 30, there's lots of ways we can go about factoring 30. 2 times 3 times 5, 2 times 5 times 3, etc. 5 times 2 times 3, like that. Or you could throw in negatives. You could say negative 2, negative 3 times 5, or negative 2 times 5 times negative 3. And we regard all of these as the same factorization. So it's the same set of primes up to unit multiples. In this case, the unit multiples are just negative 1. Okay, so in this language, the set of integers is a unique factorization domain. That is simply the fundamental theorem of arithmetic. And we claim that the proof we gave for the set of integers works identically for any Euclidean domain. And so we're able to prove the following theorem. Any Euclidean domain is in fact a unique factorization domain. Now the two important examples of Euclidean domains we look at in this class are the Gaussian integers, so z square bracket I. So this is then a unique factorization domain, and polynomial rings over a field. In particular, we'll be looking at fields z mod p. So any polynomial ring over a field F is a unique factorization domain since it's a Euclidean domain. So in this case, the delta mapping was the degree mapping. Okay, let's look at this a little more detail. So in the Gaussian integers, we claim it's a unique factorization domain. So what does that mean? That every Gaussian integer can be uniquely expressed as a product of irreducibles. So in your homework, you're going to explore the types of irreducible elements you can get in the Gaussian integers. And there are two types. So let's just do some examples. I could take the prime 2, and you'll notice that it's 1 squared plus 1 squared. It's a sum of two squares. And there's a trick for factoring a sum of two squares. You can write it as 1 minus I times 1 plus I. And each of these are irreducible. So you'll do this in your homework. You could take the prime 5 and write it as 1 squared plus 2 squared. And so that would be 1 plus 2i times 1 minus 2i. And each of these factors is an irreducible element in the Gaussian integers. Now if we started with the prime 3, you can't express 3 as a sum of two squares, and consequently it follows that this is already irreducible in z bracket I. So you can't factor it into a product like you did with 5 and 2 up here. And it turns out that this really describes the whole situation. So if a prime is a sum of two squares, you can break it up like this as a product of two irreducibles in Zi. And if it's not a sum of two squares like 3, then it's an irreducible element in Zi. And that pretty well characterizes all of the irreducible elements in Zi. So I'll let you work out those details in your homework. And then for the polynomial rings, this should be a familiar theorem from algebra. Irreducible elements are just irreducible polynomials. That is, polynomials of positive degree that cannot be expressed as a product of polynomials of smaller degree. So the example I just stated on the previous slide we can state as a theorem here. It's the unique factorization theorem for f bracket x. So if f is a field and little f of x is a polynomial over f of degree at least 1, then f of x can be expressed as a product of irreducible polynomials, and this expression is unique up to order and unit multiples. And you've probably seen this result proven in an algebra course, but I want to view both of these results as a consequence of them being Euclidean domains. So let's just outline what's going on in the proof of our theorem that says every Euclidean domain is a unique factorization domain. So there's two parts to that proof. One is the existence part. So if you're in a Euclidean domain, why is it that every element can be expressed as a product of irreducibles? And this just goes back to how did we do it for the integers? So it was an induction proof, using the strong form of induction. So recall that in a Euclidean domain, we have this delta mapping that has this property that delta of A is less than or equal to delta of A times B for any elements in your domain. In fact, you can prove a little stronger statement. You can deduce it from the two properties in the definition of Euclidean domain, that delta of A is strictly less than delta of A times B for any non-unit B. And 2, you can show that delta of U equals delta of V for any units U, V, and R. And so by combining 2 and 1, this common value that all units take on is the minimal value that delta will take on over all elements of R. So when you're doing the induction proof, you would start with this minimal value that delta takes on, and the theorem is trivially true for that value because these are just units. You don't need to even consider the factorization. And then you proceed to the inductive step. So you assume that all objects where the delta value is less than a given n can be expressed as a product of irreducibles. You consider a new object whose delta value is n, and then there's two cases. If that object is irreducible, you're done. And if it's not irreducible, well, it's a product of two things whose delta value is strictly smaller. And then by the induction assumption, you win the game. So you can work out those details if you're interested. Now, for the uniqueness part, again, we just repeat the sequence of lemmas we went through to prove that Z was a UFD. So how did we do that? We got started by proving a GCD-LC theorem. So you do the same thing for a Euclidean domain. You prove that for any A and B and R, there exist elements x and y such that ax plus by is the greatest common factor of A and B. And you can do this because we have a Euclidean algorithm. That's what a Euclidean domain really implies, is that you've got a division algorithm, and from that you get a Euclidean algorithm for calculating GCDs. Second, we deduce Euclid's lemma from the GCD-LC theorem If D divides AB and GCD is 1, then D divides B. And then we went on from there to prove that for any irreducible element, so in the case of Z, any prime, if P is a divisor of A times B, then P divides A or P divides B. So any irreducible element satisfies the algebraic definition of being a prime. And then finally, by induction, you then prove that if P is an irreducible, it divides a product of, and it divides a product of K objects, then it must be a divisor of one of them. And that was really the launching pad for proving uniqueness. Once you have this result right here, you can prove very quickly that if you have two different factorizations, they have to be identical. And again, I'll leave the details for you to work out as an exercise. Okay, now there's a more general type of domain that has unique factorization, and those are called principal ideal domains. So a principal ideal domain is an integral domain D in which every ideal is principal. That is generated by a single element. And so we represent it with parentheses around A, and this just denotes the set of all multiples of A. The set of all objects X times A such that X is an element of the domain D. So we've already seen this example here that the integers are a principal ideal domain. Indeed, we proved that we saw that every subgroup, additive subgroup of Z is of the form D. So D times Z, set of all multiples of some fixed element. And ideals are in particular additive subgroups. So every ideal in the set of integers is of this form. Theorem. If D is a Euclidean domain, then D is a principal ideal domain. If D is a Euclidean domain, then D is a principal ideal domain. The proof of this is based on the following lemma. And again, we'll leave the proof for homework. These are results that are very standard results in any abstract algebra course. Suppose that you have an ideal in a Euclidean domain, and that A is a non-zero element of the ideal with delta of A minimal. Then I claim that I is generated by A. So it's the set of all multiples of that fixed element A. And this is an easy consequence of the division algorithm that exists in a Euclidean domain. So this is the key tool for proving that any Euclidean domain is a PID. So if you give me any ideal, all I do is I pick out an element with delta A being minimal, and that ideal is a principal ideal generated by that element. Okay, so principal ideal domains are a more general type of object. Euclidean domains are a subset, and it turns out that any principal ideal domain is in fact a unique factorization domain. So it's a more general type of unique factorization domain. And I'll just state this result here without proof and leave it to the algebra courses to go through it. So if D is a PID, then D is a UFD. And so altogether we have the following implication. If you have a Euclidean domain, then it's a principal ideal domain. And if you have a principal ideal domain, then it's a unique factorization domain. So UFDs are the biggest collection of things, and Euclidean domains are very special examples of UFDs. So you might ask, are there UFDs that are not PIDs? And are there PIDs that are not Euclidean domains? And the answer is yes to both of these questions. For instance, Z bracket X. This is a unique factorization domain. But not a principal ideal domain. Again, I'll let you ponder that and think about the details as an exercise.